perfect timing. So welcome to episode 22nd. Yeah, it's the Boo Danub. Yeah, from John Strauss Jr. Yeah, so this is the kind of music usually people play at home towards the year end or towards the new year. Okay. Hi, Jayo and Jessica. Right, and yesterday I was playing Nutcracker, which is also something that people typically attend to during the new year. Yeah, from Tchaikovsky. Okay, good. So you know what? Let's go ahead and start. So there's nothing more but hi Shanting. There's nothing more to saying the to-dos. But yesterday, Boris has kindly reminded us that PA8 is doing, but next Saturday. And it is probably the least trivial PA in the second half, the lower semester. So I think it's a good idea that you guys start early. All right, and morning Yunqi, morning Juan, and morning Livia. So today, we'll start from buffer management. Okay, hi Li Jun. And there will be actually 4 videos in buffer management because it seems like just some space inside a router. But it's actually more complicated. Yesterday you heard that there are multiple components in a router. There's input port, right? And then switch fabric. And then there's also output port. So anywhere that you find that there might be a mismatch in the input rate to the output rate, you need a buffer space. Okay, so at the input port, there is some buffer space, and there could be queuing delay. There could be packet drop. But you see also between fabric and the output port can go slower than the fabric. It can happen. So you need also buffer space there. And you might have queuing delay there. You might have packet drops there. Okay. So even though one router is one router, previously we've talked about that there's a buffer space in the router, but that buffer space is actually integrated representation of multiple buffer spaces in various components in a router. Okay. So the first video is more related to the fabric. Okay. And it's more about how the output buffer can take packets through the fabric from the input port. Okay. There's one very important mechanism needs to be implemented in a router. That's called the buffer management. We'll need it in the input port as well as output port. Now, the reason that we need it in the input port is this. When the switching fabric is slower than the input port rates combined, packets coming in really fast, then these packets might need to be queued temporarily at the buffer. That's why we see queuing delay. When the buffer is full, packet get dropped. So the queuing strategy and the dropping policy, as well as how much buffer we should allocate to this input port, those things are all part of the buffer management, which we'll talk more about in the next few slides. Before that, let's talk about this very special kind of queuing delay. It's called the HOL blocking. Okay. Now let's focus on the scenario. Okay, it's easier to understand that way. Okay. So this router here I'm illustrating has output port contention. So this is one special type of router. What it means there is each output port can only draw in one packet at a time. So this red port here is only taking in red packet, and it can only take in one red packet at a time. Similarly, for the blue port, taking in blue packets. Green port, taking in green packets. Now, the input ports, there are 3 of them. Input port number 1 here has a red packet at the front. Input port 3 here also has a red packet at the front. Now, this is what? An output port contention based router. So we can only pick one of these to accept into the output port. Let's assume this one goes through and this one gets blocked. Okay. One packet time later, you see this red packet arriving at the output port. That's why we see the red packet here. This blue packet arrives at the blue port. That's why we see the blue packet here. But this one stays. Therefore, one packet time later, this red packet stays. But if you consider this case where the green packet's at the front and the red packet's in the back, then we could have what? One packet time later, the red packet, blue packet, as well as the green packets, all three of them move to the output port. So instead of receiving only two, we could have three packets through. Isn't that better? Yes. So green packet in this scenario here, it gets blocked unnecessarily when they can really be moving forward. Okay, so that is called the head of line blocking. Green packet here experiencing a head of line blocking, head of line queuing, because other packets such as the green one is blocked by the red packet at the front. Okay, and somehow the output port is not accepting multiple packets coming in at a time. On the other hand, if you have a router that implements the non-output port contention mechanism, then we could have what? Input port 1, input port 3, both have red packets. They can now all go to the red output port. So one packet time later, you see two of them here. Okay, and the blue one will also go one packet time later. Okay. And the next cycle, then you see green, the next one in line in input port 1 goes to the green port, and the red packet here goes to the red port. Okay, so HOL blocking only occur in the output port contention type of router. So that was the divergent. Speaking of this very special type of queuing one might experience. Now let's come back to buffer management. Okay. We need also buffer management at the output port. Okay. And this is because the arrival rate through the fabric could exceed the output line speed. All right. So switch here super fast, such as a non-output port contention router. Usually the packet can come in real quick. We could have red here, then all of a sudden we get 3 red packets coming in. And if the line speed here is slow, the buffer actually queued up real quick. It gets full real quick. So delay also gets long, and you might also have packet loss. And the buffer here also needs to be managed.
And now, next video, very short, just formally introducing what are the problems we handle in buffer management.
Buffer management in the input port and output ports are the same, so let's just talk about the output port side. So what I'm drawing here is the detail of the output port. So it looks very much like the input port, except it's being mirrored. So we do have this one here. This is where the buffer space is, and packet get queued up here. Okay. And this component is doing the link layer protocol. And therefore this one here, although called line termination, but this is where also the physical layer is implemented. Now let's focus on buffer management here. So buffering is required because the data could be coming in faster than the pace they'll be going out. Right? So when that occurs, we could drop packets when there's not enough buffer space. So what's critical here is to decide how much space to allocate to the buffer. And in case we need to drop a packet, do we always drop the incoming one, or maybe we pick one of those packets existing here? Okay, because that seems to be a bit fair, right? Because the packets get queued up here could be coming from one flow. So the later flow, if we drop, from within the queue, then it will be more fair to the later traffic. Second issue is this. So the packets will be drawn out of the queue and get onto the outgoing link. Which one do we pick? Okay, one could actually start from the first one, but one can also pick one of the packets seems to be more important and pass it out further. So, Perhaps you could have some sort of priority-based mechanism so that the packets can be classified and some go out earlier than the others. Or we might want to maintain that it's fair. Okay, so we want to maintain neutral so the treatment of all these packets will equal.
All right, so you can probably imagine, right? The next two videos, one is to talk more about buffering, the other, scheduling. So let's hear out buffering.
And the first part of the buffer management is this, determining how much space being allocated to the buffer. Yeah, the documentation says this, the buffer space should equal to the typical round-trip time multiplying the capacity. Yeah, the intuition behind this is this. It has something to do with how TCP does the condition control. You see, in TCP, data being sent, X coming back. After receiving duplicate X or waiting for timeout, then the source will discover there's a packet loss, there's a condition, and therefore slow down. All right? So router in the middle there, okay, is thinking, well, I'll need to buffer the packets long enough before the sources know they need to slow down, right? And that is at least one round trip time. And during this amount of time, there could be this much packet or this much data going through the link here. So that's why RTT multiplying the capacity here. In this example, we have the round trip time 250 millisecond and the capacity being 10 gigabits. These are very typical values, but you see also the amount of memory requirement pretty high, 2.5 gigabits. So not exactly practical. So some of the recent study actually discovered this. If all these flows going through the routers are TCP flows, okay, and if there are n of them, we could actually reduce the buffer requirement to this amount. Still, RTT multiplying C at the top, but we can actually divide it by a certain factor. The more TCP flows there are, the more we could reduce the buffer space requirement. Okay. So n here are TCP flows, n flows here are n TCP flows. The reason for this is twofold. One being, hey, TCP at the beginning is doing slow start, starting from window size 1. The sending rate is very, very slow. Okay? And there are a lot of data we send over the internet being very, very small. And so we use a very slow rate to send small data. Okay? So most of these TCP flows run in the low rate. Okay? So we are actually not using the entire C capacity. Second is this. Even though we are in the steady state, okay, these window sizes are all pushing and dropping, okay. Chances also high that we are not using the full capacity as well. Okay, so still also low, but not as low. Okay, in the slow start state, sending rate really low. Even in the congestion avoidance rate, it's actually lower than the capacity as well. Okay, so that's why we come up with the factor here. And the first part of the buffer management.
Oopsie, sorry, misclick. So I would jump to the part of buffering that I just accidentally click to another video.
And the first part of are all pushing and dropping. Okay? So that's why we come up with the factor here. The second component in the buffer management is this, the dropping policy or the discard policy. So this is needed when packet arrives to a full queue, right? So either the arriving packet needs to be dropped or one of the packets in the queue needs to be dropped. Okay, so generally, pick the next packet to discard. Okay. The most common policy is this, tail drop. So this is essentially just to drop the packet that is coming in the last, okay? Because usually those who arrive early are given priority. But you could actually change that, okay? Assign priority to the packets. Some of the packets might be less important, right? So we could classify them to lower priority. When a packet comes in with a higher priority, then we drop one with a lower priority. Third, random. Of course, one could pick randomly from the queue a packet being discarded, right? The last component is this. Yeah, how do we debuffer? Okay, which packet do we choose to transmit next? Okay, so the next packet to send on the link. This is also called the scheduling policy. Typically, we do this FIFO. Okay, first in, first out. So essentially, based on the packet, based on the order the packet arrives, we take one out at a time. But okay, one can also do this, the class-based scheduling. Okay, the way to do it is to divide the packets also based on the priority or based on the classes. Okay, and so we could assign a specific class being higher priority versus others. Or we could have them rotating turns, taking one packet from each class at a time. And we can actually allow multiple packets coming from one class at a time, and so that there are more packets coming out from a particular class. It's sort of a combination. So weighted fair queuing here, WFQ, is a combination of the priority and round robin. Let's go into each one of these a little bit more. So priority-based scheduling. So we send always the highest priority packet out. Okay, so when there are multiple classes, okay, with different priorities, so we send out the one always with the higher priority. If there are no packets existing, then we take whatever we have. So here's an example. Packet arriving, some being red and some being green. Green packets are the one with the lower priority, while the red ones are the one with the higher priority. So the way it works is going to follow this timeline here. So a packet is arriving at this particular time. Okay. And so there'll be some time it takes for the packet to be served. And then after they finish serving, packet exit. So yeah, let's say packet 1 arrives here. All right, so right there, packet number 1 being served, and it's going to take some time here. At this point, packet 1 will exit, but there could be other packet arriving while we're serving packet 1. So 2 and 3 arrives here. But 2 is carrying a lower priority, while 3 here carrying a higher priority. So in priority scheduling, which of these 2 versus 3, will be scheduled next here? Always the one with the higher priority, which means 3 here. Right? And then next 2. Now, while we serve packet 2, if packet 4 arrives, yeah, right after packet 2 exit, we enter and serve 4, and so on and so forth. Now, if we do round robin, okay, the rotation-based, class-based queuing, we do have multiple classes, but we do this cyclical scan, okay, of different class queues and send one at a time. So the same pattern, 1, 2, 3, 4, 5 packet arriving at these point in time. But this time, okay, the second packet is higher priority, third packet lower priority. So which one do we send next? We actually send packet 3 because it belongs to the other class, not necessarily lower class, but the other class. We have to rotate. Therefore, after red packet is served, we serve the green packet. Now, because the next rotation is red packet again, so we take packet 2. Now, the next one should be green again because there's no green packet at all, so we serve packet 4, and so on and so forth. Last is the combination of priority and round robin, so weighted fair queuing here. Okay, so this is a generalized round robin, and it's almost like having some level of priority here. You assign weights to different queue. So weight number 1, weight number 2, and weight number 3 here. Okay, so in one round, we could draw 2 packets out of the red queue, and 1 packet out of the green queue, and 3 packets out of the blue queue. Okay. In the second round, 2 more, 1 more, and 3 more, but because there's only 1 left, so we just get 1 more out. So this is weighted fair queuing.
All right, so relatively straightforward, isn't it? Essentially, for the buffering, you need to decide when packet enters where you position the packets. Okay, when it's full, you need to drop. Where do you draw packets being dropped? Similarly, when you serve packets, okay, scheduling mechanism is deciding which packet you serve next. We now switch gear a little bit, so we are kind of exiting the hardware components of inside the buffer and come back to talk about the packets that we need to forward in the network layer. So those packets we now call the datagram. Okay, and every time when we need to talk about packets, we need to talk about the header. Okay, packet header. So next topic here we'll be spending quite some time is to talk about the datagram's packet header, IPv4 packet format. And the video is a little bit long. Okay, this one is about 8 minutes. Oh, you know what? We do have a question here. Why don't I address the question? It's from Bo-Zhi. I wonder that how to define the priority of each packet. That's a very good question. People have talked about this. Okay, so I think back in the 20th century, the internet engineers often talk about classifying packets because of the content. Okay, whether this is email, text-based, or web browsing versus audio, video. Because of the nature of the content. Okay. Now, usually it's whether one has higher priority versus another, it needs to be in the implementation of the application. So if this is YouTube live versus just regular YouTube, you might set a different priority bit or QoS bit in the packet header. You will actually see, thank you for setting the stage for the packet format. Inside the IPv4 packet header, there's this special field called TOS that allow you to set priority. And the router seeing that field can decide to insert such a packet in a higher priority queue. And the rest, lower priority. Okay. I hope that addressed the question. If it's still not clear, feel free to follow up and ask more. And now let's go to this 8-minute video. We'll go through the header of the datagram. It's just as intensive as the TCP header. There are many, many fields. 4.3, Internet Protocol. Now you see here the section is a little bit long, so do expect that we spend quite a bit of time here. All right, so network layer is in the middle, okay, of the protocol stack. So what I'm showing here are, again, the important functions to be implemented there. Forwarding, we've already talked about in 4.2. Routing being in the data plane, we'll only talk about it in Chapter 5. Another thing we'll talk about in Chapter 5 is this, ICMP. This is one of those management protocols. So just like routing, management is also one of the control plane functions. So we'll be talking about ICMP later in Chapter 5. So what's left in Chapter 4 is just this, IP protocol. In there, we're going to talk about this IP addresses. If you recall, in forwarding function, the traditional model actually checks what? The destination IP address. So that's definitely talk more about the address format. And in the modern forwarding, we do what? SDN. We could actually look at multiple fields in the packet header, okay, to decide where to go. So we do need to know a little bit better about the packet format. What are the header fields? So that's coming right now. Now the two most important fields, source IP address and the destination IP address, each 32 bits long. Second, the header checksum. Now the reason this is important is because we did have what? TCP or UDP checksum that would ensure the integrity of this part of the packet. What about this part of the packet, the header part of the packet? We needed a checksum here, okay, to ensure the header part is also not having any bit errors. Now let's go over these individual fields one by one. So focus on the first row now. First field, there is called the version. So the packet we are actually showing here is defining IP
version 4. Okay, so the version number, therefore, will be 4 here, always. And then 2 other fields, header length and the length. So the header length here is to tell the size of the header. And the length here, telling the entire packet size. Last field in the first row, the TOS. Okay. It looks a bit familiar, isn't it? Because when we're talking about congestion control, there's this flavor called the network assisted approach. So we did introduce one mechanism that requires the use of the ECN bits. So these are 2 bits in the IP packet header, if you recall. This is explicit congestion notification. So those 2 bits are right here, again, in the IP packet header. Now let's switch gear and take a look at the fields in the third row. Okay, first is here, time to live. So this field is very, very special. Okay, we've never seen it before, and it will probably make sense, only it's in the IP layer. Okay, so we would do this. We would decrement the value here, time to live, TTL, by 1, okay, after a packet passed through a router. Okay. When this value reaches 0, what we will do there, this router is going to discard the packet entirely. Okay. That is also saying a packet here, given n as the TTL, will only be able to hop n routers on the internet. Okay, and afterwards it's going to be just dropped. So time to live here is kind of regulating, okay, how many hops the packet can travel on the internet. The reason we need this is because, on the internet, routing algorithms, okay, depending on how the messages are exchanged, depending on the computation process, we sometimes ended up having loops in the routes being computed. Now, in these cases, packets can actually travel the internet forever, like ghosts. Okay, so not good to have these ghosts. All right. So let's set a time to live so that they're more human-like. Right. So maximum number of hops the packet can travel. Second field in the third row, upper layer. Okay, so this is something that's slightly familiar because this is telling, okay, the network layer that after we extract the segment part, which place in the operating system we pass the segment forward. Okay, so the upper layer protocol, what is that function there? Okay, handling this incoming of a segment. Okay, so upper layer protocol to deliver the payload. It could be the UDP handler or the TCP socket handler. Now the second row. So these 3 fields in the second row are actually working together, okay, supporting each other. And it's for a very important functionality called the fragmentation and reassembly. The thing is that the IP datagram, when it enters the link layer, now the link layer actually defines a maximum packet size or maximum frame size. The packet in the link layer is called a frame. Okay? Now that size can very well be smaller than the IP packet size. So in that case, we need to cut a big datagram into smaller frames. Now these flags there, okay, are allowing us to reassemble the frames back so that we can recompose the original packet, original IP datagram. Last field, okay, here, the options. Now these are optional because it's usually for debugging purpose. For example, if we want to make sure that we track at which time point this packet traveled through a particular router, we could have the router adding a timestamp here. Okay. If we want to make sure that we know the exact path this packet is traveling through, now each router there in the middle can sign here so that we know exactly which router this packet has visited already. Okay. Now, if you sum the header size together, okay, so each row is 32 bits, so it's 4 by each row, and we do have how many rows? 1, 2, 3, 4, 5 minimum, right? So that's at least 20 bytes. So the IP packet header itself, 20 bytes. Now we didn't count the TCP packet header explicitly, but it's also 20 bytes. Right? So that's at least 40 bytes of header, okay, in a packet. Now if we are sending data that's very, very short, like 3 bytes, 4 bytes, the overhead, okay, of sending data with large header like this can be pretty high. Okay, so one of the problem in IPv4 is that the packet header there contains fields that might not be really necessary. So later you will see in IPv6, they will try to make it as concise as possible.
All right. Good. But there's something that we are yet to talk about, which are the 3 fields in the second row, fragmentation and reassembly. It's actually a very important function that is happening all the time. So check out this next video. Only slightly shorter than the packet format. So this is about 7 minutes.
So that is the IP packet format. There's one thing we're yet to talk about, the fragmentation and reassembly. Remember the second rows of the header fields. So those fields are related to this function, fragmentation and reassembly of the IP datagram. The reason we need this is this. Okay, packets, okay, as they travel the network, they might go over different network links. So for example, packet traveling the network like this. Now this could be an Ethernet link, this could be an optical link, and this could be yet another optical link, while this is another Ethernet link. So these packets might be going through different link layer technologies, running different link layer protocols. In those protocols, they might have different MTUs being defined. So this is the maximum transfer size, essentially the maximum packet size at the link layer. So different link types, different MTUs. Some of these MTUs can be smaller than the IP datagram size. In this case, we need to break the IP datagrams into smaller parts before passing out to the link layer. Now, some of you might be thinking, wait. Hey, didn't we do something like this in the transport layer, right? We take messages from the application layer, break the message into smaller parts, add the transport layer header, and that form a segment, and we pass it down to the network layer. At the network layer, what do? We break the segment into multiple parts, add the IP header, and then pass it down to the link. So why didn't we just do that, right? Because then at the link layer can just break the datagram, right, into parts and add the frame header, and such that it's smaller than MTU. Problem solved. You're right. It's just that the link layer protocols here. They are all quite primitive, and there's a good reason for that. That is because we do want packets to travel really, really fast on a link. Okay. So link layer protocol does not do the segmenting datagram implementation. So that's why the network layer there, okay, poor network layer. The network layer needs to break segments apart for the transport layer. The network layer also needs to break the datagram apart for the link layer. So fragmentation reassembly is actually to do the link layer's job of breaking the datagram apart and reassembling them back. Now let's see how it works. A large IP datagram needs to be divided into multiple parts. Okay? When we run into a link that defines a smaller MTU. Okay, so one datagram will become several datagrams like this. Note that these smaller ones are not frames. These smaller ones are IP datagrams. All right? So we actually break them into multiple parts before passing it on this link here. Now, these datagrams will remain the way they are through the network and comes into destination. The reassembly is only done here, only at the destination. So only the final destination is doing the reassembly. Okay. Now the breaking of the original datagram to multiple parts and the assembly reassembly of the multiple parts back to the original datagram is relying on those 3 IP header fields. Let's go over an example to showcase the 3 header fields: ID, fragmentation flag, and offset. The example says we do have a large datagram for 1000 bytes, and we're running into a link with MTU being 1500 bytes. So let me show you the result, okay, straight. So this large datagram is now fragmented into 3 smaller datagrams here. Okay. And so 1500 is the maximum transfer unit size. So each, less than 1500. You see there, the 3 smaller packets will all be carrying the same X. Yes, you're correct. So X is there. So the ID field there is used to identify which of these packets belong to the bigger, okay, datagram originally. Second field, you see the 3 are in sequence. First, second carries the flag 1. Only the last one carries the flag 0. So the one carrying the flag 0 is the ending packet, ending datagram. Now, these 2 would both be carrying 1, saying that they are actually earlier datagrams. But which one goes first and which one goes second? You can actually look at the offset. Okay, those carrying smaller offsets are earlier. In fact, what the offset is saying is the position of the first byte here in the original data packet. Okay, so first byte here is the original byte 0. Okay. First byte here is the original byte something. Okay, it's not exactly 185. It's actually 185 multiplying 8. Okay. So the offset is actually counting 8 bytes at a time. Okay. So that is a way to try to make sure the offset field is a little bit narrower. Because then 1 byte packet, that is just not making sense. All right. So there, you get it. This is IP fragmentation and reassembly. Okay. Oh, and by the way, okay, if you multiply 185 to 8, you get 1480. And that is because of this. Okay. There's only 1480 data bytes in the first packet. Because, hey, IP packet header is 20 bytes. So total length being 1500, data can only be 1480. Right? So as I mentioned, 185 is indicating the position of the first byte in the packet. But the position should be divided by the A. Okay, the original position divided by A will be the offset value. Therefore, offset multiplying by A, the original position.
All right. So that was fragmentation and reassembly. We move on to the addressing. Because we see in the packet header, there's source and destination IP address. Okay, you guys have seen enough of these IP addresses. Even so, for the PA assignments, you need to log on to the server. Now, exactly how the addresses are formatted, this is coming up in the next video. This is also a little bit long, about 9 minutes.
IPv4 addressing. Well, it's actually quite simple because you guys all know, right? The IP address is 32 bits long, like this. And the way we represent an IP address is more. Take 8 bits at a time, convert it from the binary form to the decimal form. And separate these 4 numbers by 3 dots. So, an IP address. And we actually say that, hey, each machine here is assigned an IP address. Yeah, it looks like it's indeed the case. Okay, but no, that's not quite precise. An IP address is actually associated with a interface. So each network interface requires an IP address. The tricky part is just this. Okay, a host here, okay, being at the end of the internet, at the edge of the internet, There's usually just one connectivity, therefore there's only one interface, therefore there's only one IP address. If you look here, routers being inside the core of the internet usually have multiple connections to the rest of the internet, therefore multiple interfaces. And you see here, a router can be assigned multiple IP addresses. All right? So routers typically have multiple interfaces while hosts typically one. Nowadays we do have two. Okay, that is why the reason for that is because sometimes if we do have wire network access, then we can plug in to Ethernet, for example, conveniently. In case now, we can still use Wi-Fi. Okay? So regular hosts, we do have two physical interface cards, but we use it one at a time. Okay? So this is an end systems characteristic. The core systems router, definitely multiple interfaces. Okay. And you see a little bit more clearly that the interface is the part that connects a host, okay, to a link like this, to a link like this. Okay. So bottom line, IP addresses are associated with interfaces, not a physical machine. Now, yeah, we did not print any of the links here, right? We did not show any of the links there. Okay, so how these interfaces are interconnected through the links. And we'll talk about the links in chapter 6 and 7. So this is the wired link and this is the wireless link, like this. Okay, this is the wired link and a link layer protocol called the Ethernet. This one here is a wireless link. It's the Wi-Fi protocol. Something else about the IP address you should have a rough sense about is this. You might have seen that the machines nearby, okay, the IP addresses for their network interfaces might look alike, especially the first, few numbers. So 223.1.1 seem to be shared by these interfaces that are physically connected. Yes, those interfaces that are physically connected to each other belongs to a subnet. So the first few numbers there, okay, is called the subnet part of the IP address. And the last, okay, that are unique, so we could separate the different different interfaces, is the host part. Those are the bits to the right, okay, the lower order bits. Now, only the interfaces that are physically connected, then they will share the same subnet address. Okay. So this is subnet 223.1.1. This is subnet 223.1.2, and this is 1.3. So each of them is a subnet, but these two are not in the same subnet because there's a router intervening. Now, we also use something like this to say, yeah, this is the subnet address. So subnet address. So you see here, this number is to indicate how long the subnet part of the IP address is. So 8 bits, 8 bits, 8 bits, 24 bits. Similarly, then the 223.1.2 subnet address is looking like this. And this is 1.3's subnet address. And what I'm teaching you here is there is an easier way to tell how many subnets we have here. Okay? Because if you want to assign the subnet address, if you need to decide how long the subnet part of the IP address is, you do want to know, right, inside your network, how many subnets there are, and inside each subnet, how many machines there are, or how many network interfaces there are. To determine the number of subnets you have, you need to detach each interface from its host or router. Okay? As a result, it's going to create an island of these isolated networks. So let's detach host, 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 router, host, 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 host. So we get what? One island of these network interface cards. One island of these network interface cards. and another island of the network interface cards. So each isolated island is a subnet. So if you want to figure out how many subnet there is for this network, break all these hosts and routers. Okay. So interface, physically connected, we have one up there. So subnet 223.1.1. We do have another one here, these three, and another one here, these three. And guess what? Another one here, right? These two together form an isolated island. Another here and another here. So we together have 6 subnets here in this network. Until now, all these subnet addresses, we see this part being 24. But this is not quite true. Okay, to be more formal, the subnet part of the IP address can be arbitrary lengths. So the general format is looking more like this. Okay, the IP address on the left, and then an X, a number on the right. This indicates the number of bits in the subnet part. So in this example here, we do have the subnet part being 23 bits long. Say the blue part, only 23 of them. Therefore, the host part, we get 9 bits. So we could accommodate up to these many individual hosts. We could allocate these many individual IP addresses to these hosts. Now, if you have a subnet, okay, that has a number of machines, okay, higher than this, you will need more bits. So this guy here might need to turn black, okay, and we need to use a length of, for example, 22. Now, one last thing to talk about is this. How do we write the ABCD out? Okay, so this is how it works. Okay, take the IP address in the subnet, okay, and then convert them to binary form. Write it out. Okay. And then cut that IP address right at, okay, the part that's separating the subnet and the host part. So essentially, cut there right after the 23rd bit. Turn all the host part of the IP address into 0. Okay. And then convert this octet back to the decimal, this octet back to the decimal, the whole octet back to the decimal, and then the whole octet back to the decimal. Okay. So if you have an X here, smaller than 24, then this last number here is always going to be 0. Right? Because it's always cut earlier here. All these bits will be 0. Therefore, this is 0. Now, as to whether this is going to be 0, well, it depends on, the subnet part. It could happen that all these, the subnet part is also 0, then you have 0. Okay. Otherwise, you're just resetting only the host part to 0 in order to write the A, B, C, D out. And that takes us to an exercise.
So that would be quiz 32. The top part is just the example we just saw. The bottom is the question. Okay. So if I do have a subnet address, the binary form looks like this: 11001000, so on and so forth. And you see here the yellow part, the subnet part, is actually longer than the example. How do you write the subnet address in the A.B.C.D/X form? Okay, so exercise what you just heard from the video. And you know what? This is also time that we take a break. So why don't we take the break in the meantime that you guys try to find the teammates and work on this. Okay. Oh, okay, good. I see that you guys are already trying to type on Slack. So maybe I switch to the Slack space. And you guys can work on this and while we take a break. This is 11:09. We'll resume the lecture and check on your Slack answers on 11:19. Okay, so let's break. so good. So I actually checked all you guys' solutions on Slack. Yeah. This one is very sort of simple, straightforward. You just convert each of the octets back to decimal. Very well done. And the total number of bits for the subnet address is 25. Okay. And so that we can move on. The next topic. Okay, by the way, you probably discovered already that in chapter 4, the topics are actually less related, although they all belong to the network layer. But in chapter 4, it's a lot of smaller topics, okay, one connected to another. So this one coming up is DHCP, because this is typically the protocol we use to get an IP address as a user walking to a new environment, walking into a new subnet. So let's take a look at the introduction video.
Let's talk about how a host gets an IP address. There are two ways, especially in the older time. You have to talk to the system admin first. System admin is going to give you the IP address. And then you manually type up the IP address at the specific place in an operating system. Now, how you do that can change from operating system to operating system. Where you do it exactly could also vary within the operating system from version to version. And some of you might need to reboot, okay, the machine as well in order to have the IP address taking effect. So this process here, the manual approach, very tedious, out of fashion. More fashionable today is to run DHCP, the Dynamic Host Configuration Protocol. What it does is to get the host and IP address automatically and configure it automatically. The service is entirely plug and play, so there's no manual effort required. Really nice. And we're using it every day. This DHCP protocol is already part of the protocol stack and part of the operating system. Part of all the operating systems these days, including the mobile phone operating system. So, formally, let me introduce DHCP. It allows us to acquire IP addresses dynamically. So what happened there is that our side of DHCP is running the client process. The subnet you'll be joining, okay? The server process is running on the subnet, running on one machine on the subnet. So the two sides, client server, will negotiate and reach an agreement. So that agreement is actually a lease on a specific IP address. And that's why my host here gets to use a specific IP address. So with this, we bypass needing to communicate with the system admin, a real person. And the assignment is also automatically done because it's all part of the operating system. But essentially, okay, after the negotiation, we get to use an IP address. But as you see here, it's a lease, meaning the IP address is also temporarily allocated. So that is why it's called the dynamic host configuration process. It only runs for a while. If you leave the subnet, this IP address will be reclaimed by the server. But don't worry, as long as you stay in the subnet, stay connected, stay on, then you get to reuse the IP address. And this is done by exchanging messages again between the client and server. So there are some more messages being exchanged and periodically so that we could renew the initial lease. So that is generally how the DHCP works. You see, this is really, really nice for us in living now a very mobile lifestyle. And the process is very simple. This negotiation process is very simple. A very simple four-way message exchange. And an even simpler version is just two-way exchange. So these two first messages, they can be actually bypassed. If the user is coming in and out really fast, typically the OS on a smartphone implements more this version of DHCP. Now let's take a look at the scenario and go through these 4 messages in a bit more detail. So here it is. We've used this network already earlier to explain, right, what's IP address format and what is the subnet address. So let's assume we set up a DHCP server here connecting to 223.1.2 subnet. And we carrying a laptop, okay, running an operating system with the client process already running. So the arriving client process here, server process here. The first message, DHCP discovery. What it does is the client asking, in a broadcast way, yeah, is any of you guys the DHCP server? So if we look into the packet, you should see the source looking like this, a null IP address. And the DHCP client is default on port 68. The server, on the other hand, on port 67. Destination will be going to the DHCP server. But hey, the client doesn't know if there is a DHCP server in the first place, not to mention the exact IP address. So we're sending it to here, the broadcast IP address. A message carrying such an IP address is going to be received by all hosts on the subnet. Therefore, DHCP server being one of the hosts on the subnet will definitely receive the discover message. Why I address here? Yeah, this is the field to store. The IP address potentially will be assigned to the client. Now, the client has no clue, therefore, it's null. Last is the transaction ID. Now, this is actually quite critical. Usually, it looks like a random number. Okay? Different clients will actually send discover messages carrying different transaction ID. Now, these IDs are also to tell the arriving clients apart. So there could be other clients arriving as well. And they could be sending these DHCP discover messages about the same time. Servers sending responses, DHCP offers, okay, about the same time. How does this guy know which offer is for this guy, and how does this other guy knows, right, which offer is for him? So transaction ID, okay, typically different, coming from different clients to enable the clients to tell whether the reply is coming for the host or not. So very important. And to respond to the discover message, the server sends the offer message. Okay, so this is saying, yeah, I'm here. And here's an IP address you could use. And inside the offer message, you see the source being the server's IP address. Destination, again, the broadcast address, because arriving client doesn't have an IP yet, but will still receive a message going to the broadcast IP address because everyone on the subnet will receive such a message. And we see here, the server is offering this IP address to the client. Transaction ID, yep, the same pair. So this offer is for this discover message. And you see, server here, while offering a specific IP, is also saying, hey, client, you get to use this IP address for 3,600 seconds long. Okay, so it's the duration of the lease. Client then say, yeah, DHCP request, okay, I'm going to take the IP address, and this is the content. Asking for this IP address, and it's a new transaction for this long. In return, the server sends back ACK, okay, which is simply saying, okay, you got it. Okay, therefore, you see, you got the IP address for this long. And this, again, corresponds to this, okay, not to be confused with other clients requesting for other IP addresses. So this is the exchange of the 4-way messages in DHCP service. Now, in the exchange, DHCP server actually say more, okay, not just the IP address, but a whole bunch of other things that are very critical setting up, okay, the subnet on the hosts. So first is who the first hop router is, because the host message is going out onto the subnet. The default next hop is always the first hop router, because the first hop router then, after picking up, then can determine where else to forward it further. Another important information, DNS servers. This is very critical, right? Because you're requesting www.google.com or www.something, okay, by the name of the server. Okay. In order to know the IP address, you also need to configure on your host the DNS servers. Okay. I know some of you might have some DNS server IPs assigned already, configured already, but if you connect to DHCP server is going to also, okay, add some IP addresses into that part of the operating system. Okay, so the name and the IP addresses of some DNS servers by default. And then the network mask. So this is to tell the host how long is the subnet part of the IP address. So provided the IP address, the HCP server is also saying that, hey, what is the subnet part? And therefore, okay, the client also know what is the host part.
All right, so that was DHCP. We'll look at a specific example and exactly the messages inside the messages that is being exchanged.
And to illustrate, you see in this DHCP example, host is right here. Okay, we just joined. And DHCP server is already up, and it happens to be running on the first hop router. So what happened there is, the connecting laptop is going to send a DHCP request message out to the network. So this is the simplified version of DHCP. Sending request and server sending ACK. So the laptop here is asking for its IP address. In addition to that, first hop router, DHCP server, and netmask. So DHCP is actually right here, an application layer protocol. And that DHCP discover or DHCP request message is going to be what? Passed to the UDP and adding the UDP header, push down to the network layer and adding the IP header, and push down to the Ethernet and adding the Ethernet header and trailer. So the HCP request gets encapsulated into an UDP packet, further into an IP packet, further into an Ethernet frame. So DHCP is actually implemented at the application layer. Just like DNS, seemingly a lower level functionality, a general functionality, okay, for everyone on the internet, but implemented at the application layer. Complexity at the edge. And it's using UDP as the underlying transport layer service. Now this frame, carrying destination address being broadcast 255.255 all the way, is going to reach all the hosts on the subnet. So this is the entire subnet. By the way, this is an Ethernet switch. It's a rectangle, not quite a circle, so this is not the router. Okay, so this is actually the link. Okay, so this interface and this interface are connected through this link. So every host on the subnet is going to receive the DHCP discover message. So therefore, the server here is going to pick it up. So this is what going to be extracted, and pass up to the IP layer. This extracted, pass up to the UDP, and this extracted, and eventually reaching the application layer. So the server then can see, this is a request message, therefore send back a reply. So you see here, going all the way, Ethernet gets demuxed to IP, to UDP, and finally, server side of DHCP. Now, the server then will generate the ACK message containing the IP address of the first hop and the IP addresses of the DNS servers, and so on and so forth. So, process is very similar, encapsulate to UDP, encapsulate to IP, Ethernet, and destination address being broadcasted. The host here, although not having a specific IP address, is going to pick it up. So client now knows the IP address of itself, name and IP address of the DNS server and the first hop as well as what? The network mask. So what I'm showing here is the result of sniffing DHCP messages. This is a DHCP request message, and this is a reply of that. Earlier we actually called it the ACK packet, okay, ACK message. And I can use tools like Wireshark or TCP dump to sniff packets travel the internet. Now, after sniffing, you're gonna see the content inside the packet. So what I'm showing here is, yeah, this is the request message. So you see boot request. And in the reply or in the ACK message, you see it says boot reply. And you see transaction ID, yeah, transaction ID, and they're identical. So this ACK here is for this request. And then you see also specifically the client not having an IP address, but it still have a MAC address. So that MAC address is actually hard-coded into the network interface card that came with your machine. Okay, so that is already existing. And that is something that the DHCP client is going to send to the server. So server can identify you somewhat by the MAC address. And then, yeah, this is DHCP request, okay, and this is DHCP ACK. And the client is asking for these, right? So the IP address, okay, so IP address is not clear yet. So requesting, yeah, this IP address. Okay, so this is not a sure thing. It's just that the client suggesting, can I get this IP address? And it's also asking for, yeah, domain name servers, and the subnet mask. Server here, yeah, in the response, you will see, okay, hey, client, okay, it's okay to use this IP address. Go ahead. In the meantime, it's returning also the subnet mask, yeah, the first hop router, as well as the IP addresses of the DNS servers and the domain name. So all these information, client can then set everything up and then begin to access the internet.
All right. So that was DHCP, now with lots of details. But those who are keen, you might see also that DHCP assigning IP address. IP address is actually a notion in the network layer, right? But DHCP is what? An application layer protocol. It's running on top of UDP. Recall, DNS service. Yeah, it's to provide translation from hostname to IP address. It is, right, because it's telling the IP address. That is, usually people think a network layer function, but DNS is implemented as an application layer service running on also top of UDP. Okay, so why? Very good. We leave the complexity to the edge of the internet, all right? So DHCP is something, again, a little bit similar to DNS. In fact, it's even more fundamental than DNS because DHCP is to tell you the IP address to begin everything with. Okay, because afterwards, then you can send the host to IP request through the DNS server that DHCP reply tells you. Okay, so DHCP just as important as DNS service and probably more important. Okay. Oh, and we do have 2 questions here because DHCP is something that we use every day and probably all the time each day. Okay. Chunmao is very sensitive to, I guess, security issues of internet. Can one grab the DHCP request message and send the false IP address back? Well, you know what? It's very possible. This is actually rather easy to do. I mean, if I joined a subnet earlier, I would have received a reply from the DHCP server default on the subnet. And of course, I can try to mimic what the DHCP server is doing and assign IP addresses by sending fake reply to the newcomers. Okay. So yeah, of course, it could create some trouble to the subnet, especially for newcomers want to access the network. So one can easily pull a DOS attack by pretending to be a DHCP server and randomly assign IP addresses that will collide with other machines on the subnet already. So Chunmao, very good observation. This can probably be prevented by encrypting the content in the message exchange. So more secure DHCP implementation. Another thing is that this kind of attack, I would say that it's a little bit harder to do unless the attacker have, physical access to the area. For hackers on the internet, this is the kind of attack that they will prevent doing because they get caught easier because of the security cameras. Okay. Very good question, Chunmao. And I think Boris is asking, I wonder the components decide subnet part. Which components decide the subnet part? You know what? That is a very important component. That component is called the network admin. So there is a person there, okay, deciding, okay, for my network, how long the network part should be, the subnet part should be, and how long the host part should be. Okay, so this admin will need to send a questionnaire to each of the department and find out that how many machines that requires unique and global IP addresses. Once they have a better idea, then they can decide what is the subnet part and what is the host part. Can the routers themselves decide for themselves? That is a very good question. I think the practice is more that the admin decides. So some sort of manager, human intelligence decide the subnet versus the host part. But that can potentially be done also by the routers themselves if there are some sort of intelligence implemented into the DHCP as well. Okay. But you can imagine also that because each subnet runs a DHCP, and perhaps you need to have some sort of message exchange among the DHCP servers from subnet to subnet in order to collect the information. One can definitely think about it. But I have to say, even though the network admin is deciding how long the subnet part is and how long the host part is, okay, but the subnet part cannot be shorter than how the whole institute is allocated a big subnet, a big group of IP addresses. For example, we see earlier that in the example we have 23 bits subnet address. Okay, so we say something /23. Okay, this is usually because the admin is allocated exactly this bunch of IP addresses. Okay, now admin of course can tell each of the department. With this a set of address being /24, so each department gets a part of the overall number of IP addresses. Okay, so within the /23 subnet, you can further divide the IP addresses space into the subnets, into different departments in the institute. But you cannot use a subnet address that's /22. Because, hey, you are not allocated that many IP addresses. All right. So that's the slight tricky part about deciding the subnet part. It cannot be shorter. It can be longer. It can be sent manually. I think Bin Rui is right because the practice is exactly manually set by the admin. All right. So DHCP, very important protocol. We use it every day, all the time. And we move to the quiz, which is a very open-end quiz. Okay, so you see the question is long as well. Okay, what I'm showing on the left of the slide is it's actually a news report. Okay, reporting a survey about the users of Free Taipei, Taiwan Free. There are actually quite a few of these free Wi-Fi access around. Okay, so if you look at the right side, so I translated the reporting to English. There are quite a few these free Wi-Fi access points all around. Okay, not just within Taiwan, but the survey is targeting the Taiwan free Wi-Fi access. Okay, so these are provided as a friendly gesture to travelers. But, big but, among 40% of the users that there are users that are not satisfied with these free Wi-Fi access. Okay, among all these people who are not happy with something free, Taipei free, Taiwan free, or Kaohsiung free, 74% stated the reason being this. They are not being able to connect to the free Taipei, free Taiwan, free Kaohsiung network. Only 60-ish% of the users complain that they have low connection speed, they have weak signal, or simply saying that there lacks the access points. Okay, they couldn't find free Taipei, free Taiwan everywhere on all the subway stations. Okay, so the top one complaint is we couldn't connect. We see there's a free Wi-Fi AP around, and the signal strength might be strong. Okay, but we tried to connect, and we couldn't get connected. So Q1 asks, what do you think the trouble is? Okay, what do you think the problem is? Okay, you see that these users walking to a new subnet. First thing, by clicking connect, is to try to get what? An IP address. So somehow that DHCP there for free Taipei, free Taiwan, free Kaohsiung are not allocating IP addresses to these users. Why? So Q1 asks you why. DHCP failed to work for these users. Q2, well, if you are the administrator for the subnet, how would you reconfigure your DHCP server such that it would allow a more satisfying service? Okay, it would increase the rate of random users connecting to the subnet. Okay, 2 quizzes. These are long quizzes. Think about it. Okay. See if your teammates are around. Feel free to have a discussion. Okay, you have 10 minutes for this. All right, we do have quick responders. So Team 4 says, it might be because there are just too many people trying to connect. So this is more that everyone tries to connect to the DHCP server at once, right? Too much load for the server. That could happen. I think especially, for example, in the Taipei train station, there could be like a flash crowd of travelers, okay, coming in and trying to catch a train. So DHCP server overloaded. And therefore, the solution for Team 4 is to increase the density of DHCP server. I see. Okay, that's an interesting solution because, each person occupies a certain area of space. Okay, if there are more people trying to join the subnet, perhaps we could set up multiple DHCP servers and one will cover a smaller area each, and therefore we could handle more people in the meantime. Okay, that makes sense. So here, the observation, okay, is the hypothesis is that the server load being too high. Okay, this is possible. Team 2 here is saying, okay, so let me make sure I mark this. Great. Team 2 saying this. Maybe there are not enough IP addresses. Okay. You know what? This is very possible, right? In case we only have 64 IP addresses for this subnet, and there are 100 people coming in and looking to use free Taipei station. Of course, there's not going to be enough IP address. Okay, the solution? Yeah, okay, so that's one way. Yeah, so urge people to use their own 4G network to access the internet. Sure. That's one way. It's a little bit cruel though, but that's one way for sure. Okay, Team 3. Yeah, so I guess Team 3's answer is similar to Team 2, right? If there are not enough IP addresses, then the demand. Okay, so we run out of IP addresses. Yeah, of course, you heard, right? Earlier when we talked about the IP address format. The reason that we don't have that many IP addresses is because the subnet part is long and the host part is short. Of course, we could increase the host part of the IP addresses if the admin are allowed. Okay, that many host IP addresses. Okay, that's definitely legitimate. Or the admin can ask on behalf of the demand to some higher level beings for more IP addresses. But usually IP addresses are not cheap. They are costly. Okay, Team 1. Too many people trying to connect and there's not enough IP addresses. Okay, expand the number of DHCP servers, definitely. Very good. Oops. Team 7, Jiao is saying the IP address is not enough. Can be solved by increasing the number of DHCP servers. Well, by increasing the number of DHCP servers, of course you handle the load of individual server. But to increase the number of IP addresses, you need to reset the subnet part and host part of the IP address. So in a way, the network admin need to do something else in case it's just that the IP address is not enough, okay, for the requests. Okay. Qi-en, too many people collecting and IP address is not sufficient. Increase the number of servers. So again, increase the number of servers help addressing the part that there are many people trying to connect. Okay, but in case it's really number of IP address not being sufficient, you need to reconfigure the sub network. In case you are not allowed that many IP addresses, you need to ask some higher being. All right. And we have 3 more minutes. Okay, take your time, the other teams. So can anyone think of other different causes that we sometimes have trouble connecting to the free Taipei, free Taichung, free Kaohsiung, these free networks? So anyone coming up with something different gets extra point. Let me see. Oh, okay. I see more. Okay, so team 13 here is saying that not enough IP addresses. And another reason, the servers couldn't take the load. Consider a different setting. Okay, and oh, very interesting here. Limiting the use time of the IP addresses. Okay, so Juan, you are definitely paying attention. When we were introducing the DHCP protocol, right? Because after negotiation, in the reply to the new host, we not only give the IP address, we give also the amount of time we allow this new device to use the IP address. So here, maybe we could limit the amount of time we allocate the IP address to each of the hosts. Because that way, when they're done, okay, and they are not using the IP anymore, we can quickly reclaim the IP address. And so we could assign these IP addresses to the next user. Very good, very good. Yeah. So definitely one of the tricks that we can play is system admin to the network, which is also very simple, is to shorten amount of the lease, okay, to some lower value. I think 3600 second that we saw in the example earlier, that was 60 minutes, which is an hour. That was really long, right? Do you spend an hour time in the subway station? Usually no, right? So you go to a substation as you are waiting for the next subway train. You connect to the network and check out the latest video on YouTube, and then when the train is here, you're gone. Okay, you don't really need a whole hour. Very good observation here. Okay. Team 14, Ming Hong. Too many users asking for the IP addresses. Yeah, running out of the IP address, definitely. Timeout may not be set up properly, causing the old users still opening the Wi-Fi, thus occupying the IP. I see. I think Min Hong is pointing probably to the lease. Okay, duration of the lease. Yeah, because the users waiting for the previous train just check out some of the IP addresses, but they are gone now. But those leads won't expire until an hour later. Exactly. Increase the host part of the IP address, definitely. Set the timeout timer to something that's shorter. 15 minutes, for example. That is probably the duration of the train intervals in the non-busy hours. Okay, in the busy hours, maybe a little bit shorter. Team 15 here. Shengwei. Probably too many people connecting to the network, so the host part are not enough. Too many are trying to connect. Yes, of course. Yeah, multiple reasons, right? Too many trying to, so there's a flash crowd traffic into the server. Okay, that's the team 15. Add the login page, I see, and set the disconnection timeout. Okay, so this is something different. And this is actually a common practice now, right? So when you connect, you actually have to do logging and stuff like that. If we auto connect by just clicking a subnet, it's very easy. And so the IP address gets occupied easy. So a logging process to ensure that it's a little bit harder, and so only the serious users get connected. Yes. 16 here. Oh, hi, Weijan. Too many people want to connect and not enough IP address for all, and increase the DHCP servers. Okay, good. Hi, Lawrence. Welcome back. Not being able to connect might be due to the finite address space, definitely. In those public space, there will be, yeah, they are easy used up, definitely. are connected to it. So they might just connect to it and then browse a page, for example, looking at the Google map to find out after they arrive at the destination station, which exit they should go next. And then they're done with it. They no longer use it. Yeah. So very good point here. They can stay connected, but they don't use it. They are still in the station, but they no longer need it. So maybe the time duration of the lease can be even shorter. And somehow ask the clients to send refreshing the lease, okay, when they need it. You know what, Lawrence? This is something that I run into a lot when I was doing international travel, trying to connect to the Wi-Fi in the airports. I do see that, although I'm still in the same spot, but after a couple minutes being idle, I got kicked out of it. And I need to reconnect to it. Yeah, so another, the receiver can handle the request. Yeah, so I think not using it and somehow I get kicked out of it, that is probably the network admin there trying to also maximize the utilization of the IP address they have, given that the IP addresses are costly. Increase the lease expiration, decrease the expiration time. Exactly, and probably to some very, very short time. I think potentially one could think of a way to analyze first, okay, how long the connections are usually are, or how long the users are active using the IP address, and from the history, suggest what is the best lease time. Very good point. And team 2, again, sure. Another possible problem may be the queuing time is too long. Very possible, very possible. Yeah, but yeah, because there's a Wi-Fi box, an AP there, right? Taking messages from our device. Okay, so that AP there has a queue. So once that request for IP address gets through the queue and gets sent to the server, then you can potentially get the answer back. So it could be the access point being busy. Not exactly the DHCP server, but the access point. Is that possible? It is possible. Okay, one could actually connect to the Wi-Fi. I mean, there are some users there already. They already connect to the Wi-Fi. And what if they are watching high definition videos through Netflix? Yeah, if the AP there installed in the subway station are not exactly the high-end Wi-Fi, like Wi-Fi 5, Wi-Fi 6, what if they are still the older version? Okay, the amount of bandwidth there are is not enough. Very good point, very good point. The AP might be the bottleneck, you see? So I'm very happy to see you guys, thinking deep further and trying to do detective work and find out what are the possible reasons. So you guys, if you are not quite aware of that, this is a very important skill for engineers. And the trick is just to exercise that detective thinking, critical thinking. All right. Team 12, Bing Ray, IP address in the subnet are all used. Yeah. And the DHCP server might also suffer from the traffic issue. Q2, increase the size of the subnet, if possible. Set a timeout interval that's a little bit more appropriate, shorter. Or increase the number of DHCP server. Yeah, in case the load is on the server. Okay. Or upgrade the AP, right? Upgrade the AP there. That should also work. Very well done. Yeah. You see that there are multiple reasons So that survey there is very interesting the first time I saw it in the news. And it's been a while that the Taipei Free was like that. So the company had no idea what was wrong. If they took this course and take this quiz, their engineers will know better, okay, what to do, and will be more satisfied using these free Wi-Fi access. Okay. All right, and okay. So we do have one more topic to go, but we probably have just enough amount of time to go over the introduction video about hierarchical addressing. You see, subnet and host part of the IP address, and you see also I mentioned you can make the subnet part a little bit longer and then assign each of the department within your institute a portion of the IP address. That is actually enabled exactly because of how we design the IP address space. There's a subnet part, there's host part, and the subnet part is at the higher order bits. Okay, so we just extend the size, then we get to divide the big subnet space into subnets. Naturally hierarchical. So that was how a host gets an IP address. We ask the system admin for one or DHCP server for one, which is configured by the system admin. So the bottom line is, how does a system admin get a block of IP addresses so that the system admin can assign to individual hosts? So the next question we're asking is exactly that. How a subnet gets the subnet part of the IP address? The answer is quite straightforward. As we ask the system admin for one, system admin asks the higher level system admin for a block of IP addresses. So if we are customers of an ISP, we ask the ISP for the address block. So what I'm showing here is an example. ISP owning a big block of IP addresses. Okay, so by big block, this is how big a block is. Now the prefix of the subnet address of the ISP is only 20 bits, so only up to here. Therefore, that allows us a bigger free IP address space. Now, if there are 8 customers, okay, subscribing from the ISP, organization 0 all the way to 7. ISP can further divide the bigger address space this way, extending the prefix by 3 bits. So that is pushing it further here. So 3 more bits being included into the subnet ID. Because there are 3 bits, so we could uniquely separate the 8 different organizations. But as a result, we get what? Less free IP space. Each now gets only this much. That is what? 1/8 of the original space. So we are splitting the IP address to 8 equal ways. And it is done very easy by just simply saying this, extending from 20 to 23. Let's say if organization 7 here having 4 departments and each ask for equal share, then very straightforward, right? Extend from 23 to 25, the prefix lengths. And so we'll be actually doing something like this. Take 2 more bits here, and there are 2 bits, therefore we could identify 4 departments uniquely. And the IP address space is now down to 2 to the power of 7. Okay, 1/4 of the second level organization here. So you see, using the prefix there by sliding it to the right, we actually create also a natural hierarchy in the IP address space and dividing the IP address space. Just like how human beings divide and organize bigger society to smaller society and even smaller society. So this type of addressing, the IP addressing, is also called the hierarchical addressing. Okay. There's actually one more benefit of it, not just that dividing the address space is made very easy, but also this.
we could do very efficient route advertisements. Now, routing is one of the major functionality in the network layer. We have not yet talked about it. So in order to explain how efficient this is, let me just give you a slight overview of routing.
And we'll do that next week. Okay. And coming next week, we'll also talk about NAT, N-A-T, the network address translation. Because the problem that we just went through, shortage of IP addresses in a subnet, that can also be addressed by installing NAT. Then the system admin will have infinite amount of IP addresses they can assign to the users. Okay. Well, not exactly infinite. 2 to the power of 32, that's the maximum. Okay, so come back again next week. You will hear about NAT. Now, the other extreme is NAT is taking an approach that we just use these IP address, but in a fake way. Okay, so we translate the fake IP addresses to the real IP address to enable communication. The other extreme is to expand the internet IP address space. Currently, in version 4, we have 2 to the power of 32 IP addresses. In version 6, we blow it up to 2 to the power of 128. Okay, so both of these also might address the issue we run into here. Okay, too many users and too few IP addresses. So I see you again next week. Those who have questions, feel free to stay and type up the questions on YouTube channel, or just bump in through the Google Meet session. For the rest of you, okay, go get lunch. Have a good day or good weekend. So let me resume. John Strauss, the Buddha knew. Goodbye.